Good evening, class. Welcome to class number 7 of the course Electronic Theory of Solids. In today's class, we will be covering topics which includes the quantum mechanics counterparts in condensed matter, problems which are based on the spin and the angular quantum numbers, which are crucial in determining the properties of the material, like being if they are ferromagnetic or diamagnetic or paramagnetic. So these are the topics which we'll be covering in this today's class. And having said that, I will start with the first problem, which is determining the relation between the vector potential A and the magnetic field B. So the question goes like, that uh, which of the following represents the vector potential A for a constant magnetic field B in Z direction. So the question essentially saying is that okay, let me give you the four options also. So the options are 1 by 2 bx x cap plus by y cap. Second option is 1 by 2 minus bx x cap plus by y cap. Third option is 1 by 2 minus bx minus by x cap plus bx y cap. And the fourth option is 1 by 2 minus bx x cap minus by y cap. These are the options. And so to solve this problem, first we have to know the relation between the vector potential A and the magnetic field B. So the relation which goes is like, this is the solution part. Relation between vector potential A and magnetic field B. So the relation is vector B is equals to curl of A. So this is the relation. And since in the given question, in the given problem, magnetic field B is given as Bz cap, right, in the Z direction. So this is the criteria. Now we have four options, and after the four options, we'll have to see for which one the curl of A gives B is equals to Bz cap. So let's start from option number 1. Vector A is 1 by 2 Bx x cap plus By y cap. And the curl of A goes to Ij k del by del x del by del y and del by del z. Then you take bx, by, and 0. Right? And now, if you take the determinant of it, you will get 0 plus j cap to be 0 and plus k cap to be also 0. So this gives you 0. Right? And this is not the solution because the curl of A has to be bz cap. So this is incorrect. Option A is not correct. Now let's analyze the option number 2, which is vector A is equals to 1 by 2 minus bx x cap plus by y cap. If you take curl of A, it turns out to be again the same thing, I j k. Here it should be bx by 2 and by by 2, but that doesn't change the result. Del by del x, del by del y, and del by del z minus bx by 2, by by 2, and 0. So if we take curl of A, it turns out to be I cap minus b and this is 0 essentially, yeah, minus j, this is also 0 plus k, and this is also 0. So this is also 0 vector. This one is also incorrect. Now let's analyze the option number 3, which is A is equals to 1 by 2 minus by x cap plus bx y cap. So if we take curl of A, it will be nothing but I j k del by del x, del by del y, del by del z minus by by 2, bx by 2, and 0. So component of I are 0, j are 0. Let's see the k. K is b by 2. If we take derivative here, it's b by 2, and the derivative of this will be minus b by 2. Negative negative cancel. So this is b k cap, or I can write b z cap because k and z essentially means the same in Cartesian coordinates. So curl of A we are getting to be b z cap, and this matches our desired magnetic field direction and magnitude. So this is the correct option. Now one more option is also there. We'll have to analyze that one also. Another option which we have in our question is 1 by 2 minus bx x cap and minus by y cap. Yeah. So if we take curl of A, it will be I j k del by del x, del by del y, del by del z minus bx by 2 minus by by 2 and 0. And if we solve this one, what you get will be curl of A is equals to 0. So only option 3 satisfies the P is equals to BZ criteria. So here option 3 is only correct. But let me ask you one question. Is choice of vector A for B is equals to B z cap unique? Anyone who wants to answer this question? That is the choice of vector A, which is defined like this, and A, which is known as the vector potential, for a given magnetic field direction and magnitude, is the choice of vector A unique? I see someone is typing in the chat. Yeah. So yeah, so someone is saying that it's unique. So the answer is actually no. It's not unique. And how do I prove it? Okay, let's say we have B is equals to BZ cap, and so one of the vector potential which satisfies this criteria is this, right? Minus by x cap plus bxy cap. But another one which I can think of will be, there are multiple one actually. I can create an infinite number of possibilities of the vector potential, which gives me essentially the same magnetic field. For example, let me just write another vector potential which will give me the same result, will be minus by x cap only. Another one I write to be, which will, let me call it a1, let me call it a2, bx y cap, right? So these two I have written, and let me show you that they are not unique. For example, let's take curl of a1. So I j k del by del x del by del y del by del z minus by 0 0. Now if you take the derivative of it, you will get bz cap or bk cap, curl of a1. Similarly, if you take curl of a2, ijk del by del x del by del y del by del z 0 bx cap and 0. Here also I'll get the same result, which will be curl of a2 will be bk cap. Yeah. So I have shown you two more example other than this result, right? Which tells me that okay, the choice of the vector A is not unique. For the same magnetic field B z cap, here only I showed you the three possible combinations of A, and which I can then play with more around and then can have more of it. For example, I can write one to be one more to be 1 by 2. Instead of 1 by 2, I write it to be minus by 4 x cap plus 3 by 4 bxy cap plus 0 k cap. This will also satisfy the criteria, and then I can play with the number, this number and this number, minus b by 4. Yeah, and I can play and then show that okay, there are infinite possibilities of the vector potential A for a given magnetic field B. And that's the good thing about the vector potential A, And reason why theoreticians wants to work in terms of vector potential A, because then they can choose the vector A which satisfy of course the magnetic field criteria, but it makes the calculation simpler, like by aligning the A according to the symmetry of the system. And if this is clear, let me know. And if there is any doubt in this one, please ask in the comment section. I'll be happy to answer that one also. I see someone is typing in the comment section. So let me take the comment, and after that I'll take this question number second. Yeah, okay. So this is a good question. Is the vice versa true? Like for a given vector potential, can we choose different directions of B? No, that's not allowed. Because now you are taking the curl of A has to be B, right? Curl of A has to be B. For a given vector A, if you take curl, this will give you unique magnetic field B. You can't have like different magnetic field for a given vector potential. So for a given A, vector B is unique, but for a given B, A is not unique. Is this clear? Yeah. Mm. So if any doubt is still there, you can ask in the comment section. Okay, let me take the next question, which is if the cyclotron frequency of a harmonic oscillator is Fc is equals to 1.75 into 10 power 11 hertz. And point to note is that omega, which is the rotational frequency, is equals to 2 pi Fc. The magnetic field length of an electron is, and you have to determine the number. Okay. So first we'll have to understand what the magnetic length mean, and its essentiality in terms of the quantum part of the Hall effect. Let's say the quantum Hall effect, in which these magnetic length plays the important role in terms of the screening and how the electrons are moving inside the 2D layers. So let me start by writing the term of the magnetic length, and then taking the steps forward on that to calculate the magnetic length for the given frequency and the electrons. Answer. So magnetic length is generally represented by Lb. It represents the typical radius on the circular orbit that electron follows when confined to a 2D system under magnetic field B. Okay, so if you have your 2D system like this, let's say, right, and in which electrons are there, which are moving in this direction. Let's say their velocity is in this direction initially, px I cap, and then you turn your magnetic field, which is bz cap. So now a force will be there on the electron. So let me just draw it like this: x, y, and the z cap. Yeah. So okay. Mhm. So this is y. So this is j cap. Vy j cap. Ba. This is x. This is y, and this is z. Okay. Vy j cap. This is the velocity. Vj cap. Okay. Now let me write y cap. That will be more consistent. So now the velocity which you have is by cap. Magnetic field which you have is b j cap. So the force on the electron will be minus e, that's the charge of the electron, and v cross b, that is the velocity times the magnetic field. So minus e times v is v by cap times b, and it's y times z will be x cap, right? So the force will be in the negative x direction. So the electron which are moving like this, they will encounter a force in this direction, and the consequence, they will start orbiting like this. Yeah, like this they will start orbiting, and the radii of these electron orbits, essentially, you the radii of these, essentially, you call, yeah, you call the magnetic length. Radii of these orbits is called magnetic length. And why this is important? Let's say one electron is revolving here, right? Another electron is revolving here. Third electron is revolving here. Then there is not an issue, right? They are independently uh, revolving in their region. But the thing becomes interesting for, let's say, when your magnetic field is small. In those scenarios, they might intersect also, right? These orbits, because now the magnetic field region is large. So let me just increase it slightly more so that it becomes clear what I want to say. Okay, your magnetic field is small. Now your die of these ones is large, but the number of electrons is same. So what will happen? They will start intersecting. Thereby, magnetic length is important because it tells you about the radii, LB. Let's say, and here also it's LB. So if you know your system's length, if you know system's length, let's say your system's length is, uh, let's say it's capital L, right? And you know the carrier density, and then you can determine where are they arranged in your system. Electrons are arranged, and then according to that, their cyclotron orbits where they are doing, whether they are intersecting or not, and all those information you can extract, and that comes as magnetic length, which is S bar by EB. So this is what the magnetic length is and why it is important in terms of the condensed matter. Yes, sir. Now the frequency is given. So given the parameter, now we will extract out the magnetic length. So Fc, which is 1.75 into 10 power 11 hertz, omega c, which is 2 pi Fc, is Eb by m, right? Omega c we know cyclotron frequency is Eb by m, right? So we estimate the B to be 2 pi Fc times mass of electron by charge, and that this gives you BE is equals to 2 into 22 by 7, or 3.14 into Fc, which is 1.75 into 10 power 11 times mass of electron, which is 9.1 10 power minus 31 kg. So the dimension of it will be joule second inverse meter inverse square. So BE will be nothing but 100.1 into 10 power minus 20. Right? And you can write it as 1 into 10 power minus 18 joules second inverse meter minus 2. Now magnetic field is nothing but H bar by EB. So H bar we know is 1.05 into 10 power minus 34 joules second inverse. H nu, right? It's nu is inverse, so joule second, should be joule second, and EB is 1 into 10 power minus 18. Nu is inverse of time. C is meter per second. Yeah. So this will be joule second inverse, and meter minus 2. It should be joule second here. So the joule second cancels, and the answer which you get is around 1.02 in 10 power minus 6 or minus 8 meter, which is roughly 10 nanometer approximately. So this is the length scale of the magnetic length. So the typical radii are of, if you take it to be around 5 Tesla, this is around, magnetic field is around 5 Tesla, right? If you take electronic charge to be 1.6 in 10 power minus 19, then magnetic field will be roughly around 6 or 7 Tesla. So at around 7 Tesla of magnetic field, if you keep an electron in 2D electron gas, the radii, roughly radii of it will be LB, will be around roughly 10 nanometer. So they will make a kind of lattice kind of thing with a radii of 10 nanometer. That's what it means. Is there any question or doubt on this magnetic length is? If there is any question, please ask in the comment section. I see someone is what the importance of this diagram. The orbit of two different electrons are intercrossing. Okay, so when mm, orbits of the two different electron intercross, right? Then the current makes a path. Okay, now this is a good question. So whenever this happens, let's say if your electrons are like this, 1 second, let me just select it, and then I'll show you. Okay, this is here, this is here. Maybe three more. Okay. Okay. This is one case. And then I will draw another also. So when you have electrons like this, right? And this is your source, this is your drain. So since electrons are like this at these points, so through bulk there cannot be any conductivity. Bulk, no conductivity. Right? Because electrons will revolve just here on this circle only. They will not go towards the drain. So they cannot go from source to drain. Their conductivity will be zero. The resistance will be very high. Right? In that case, that's how you think. But if you have your orbit which are like intercrossing, yeah, like this. Okay, let me just draw it some bit more. Okay, so essentially what I want to say is that if you have intercrossing orbits, what will happen you can also see here. That now from this point electrons are moving like this, right? Then they can jump on this one, then they can jump on this one, and the electron now can move by hopping, by jumping from one orbit to another. They can move along these paths, right? So electron can come like this while intersecting, then it comes on this one, then this one, this one, this one, and by doing so, right, it can reach to the drain. So if the electron goes from source to the drain, that's what we call the conductivity, right? Conductivity. So here the finite conductivity will be there, finite, non-zero. But in this case, conductivity will be zero. Conductance G will be zero. So this is what it means. And that's how these two systems are different. Is this clear? But here they cannot jump, right? If electron is moving on, let's say this one, so electron will be keep moving on this one. It cannot jump to this another orbit. How it will jump? They are not connected. But in the second case, they can, and that's why it gives the finite conductivity. And this is what usually happens if you see a quantum hole G versus nu, where you have the plateau like this. So in between, wherever these transitions are happening, these points, at these points, the magnetic field line crosses each other like this magnetic length, and they make the orbit such that electron can now move from this end to the other end. And yeah, that's all. So is this clear? Or shall I discuss more on this one? It was a really good question because it gives you a sense of what the quantum hole effect is and how do it comes, because that's where the quantum hole come, right? You have your zero, your bulk conductivity is zero, your bulk is insulator, but then you can think of, okay, I'll discuss it more slightly. Yeah. So if I just copy this one, I'll show you how the conductivity happens. Then in this case, conductivity will still happen, but its mechanism is different. So it will happen. This is source and this is drain. You have it all covered. Okay, and then this orbit, let me pick. Yeah, now we can keep it like that. Okay, now how the conductivity goes is through these orbits, open orbit. We call them open orbit. So what does it mean? So if an electron which is coming from this point, right? So inside one they can make a complete circle. But what about the outside one, which are like this? If they come at this boundary, they cannot make this circle because outside, no electron can exist outside of material, right? They will have to be inside the material only. They cannot escape the material. So they will reflect back from this point, like this. At the boundary, these semicircles will be there, right? These semicircles will be there. Uh, I have made a mistake. The all of these semicircles should be of same radii, not of different radii. So I can just, maybe I'll correct that one because otherwise it's physical picture of this is incorrect. So I'll just correct it. Maybe I'll take this one. Yeah. And yeah, yeah, like this. Or maybe they'll have to with the same dia. So I'll just bring this one down and open, increase the size of this one slightly so that it can host all of these. Yeah, so they cannot come outside. So this you just remove this one. Okay, so like this they will be there on the all full boundary. Here also they will be there. similar to this one. So now what will happen? The current which was moving like this, right? They will connect the full region like this, like this, like this, like this, like this, and then they reach the drain. So now an electron, so the current will flow from source to drain like this, I, and electron will flow in this direction, right? Electron flow in the opposite direction. So the electron will start from here, then it come on here, here, through the edge. This is what we call the edge. These are edge states, and then it comes like this and goes into the source. And so here bulk is insulator, insulator, bulk of the, I mean bulk which is the inside part of the your material, but your edge are conductor, and this you know call as topological insulator. And this is the current emerging field, current field of interest in both theoretical and experimental condensed matter physicists. Theoretical and experimental condensed matter physics. I don't know whether you guys read the archive papers or not. Archive. Out of 10 papers, almost 2 to 3 papers minimum are there on TI, topological insulator. Yeah, so this is the sense of the magnetic length and their role in terms of a new class of phase. This gives the new kind of phase to the system where bulk is insulator and your edge are conductor, and which is known as the topological insulators. Yeah. Now I think I have discussed enough on this one, and if you, in case if you have still doubt or anything to ask on, then definitely you can ask in the comment section. So having said that, I will move on to the next question, which is from the quantum mechanics. Consider the Hamiltonian. H, which is of the harmonic oscillator, E square by 2m plus half square, right? And now a constant electric field E is applied in x direction then determine the modified Hamiltonian. How the Hamiltonian will be modified? So what we have is the given Hamiltonian of a 1D system that is confined in the x direction basically. So your Hamiltonian is E square by 2m plus half kx square, right? So the first term is the kinetic part, kinetic energy part, and the second term is the potential energy part. Okay. Now a constant electric field E is applied In the x direction, the potential energy of the electric, the potential energy the electron is modified, and the modification goes as the potential energy. Let me represent it with the Vx, because it is in the Vx direction, is equals to half kx square minus electric field times the x direction, uh, position basically. So now you have your new Hamiltonian will be h prime is equals to p square by 2m plus half kx square minus and x. Right, let's try to rewrite. So this one only answers the question actually. So then determine the modified Hamiltonian, but we want to go step ahead and write it in a term such that we can write the energy out of it, so in a more sophisticated way. So h prime will be p square by 2m plus half k x square minus e 2 ex by k, right? And h is equals to p square by 2m plus k by 2 x minus e by k whole square minus e square k square e square by 2k. This is just a constant quantity, right? K is under root omega is equal to under root k by n. So this is k is constant, e is constant, electric field is also given constant. And so initially the harmonic oscillator, which was like this, where the potential energy Vx, if you draw it, it is like this, right? Half kx square. This is V initially. But now, if you write H equals to p square by 2m plus half x minus, so this is just a constant, this is shift in the energy. You can think it like a DC shift. So this is just a shift. P square by 2m is nothing but kinetic energy again, and this is new term which you can write as Vx prime. So if I draw the Vx prime, it is nothing but half k x square, you can think, right? X minus x naught to the square. Okay, let me write it like this: k by 2 x minus x naught k square minus e square by 2k. This is just a constant. So h is kinetic energy plus v prime x. In this one, v prime x, your center is shifted in the direction, in the positive direction, right? Here, instead of 0, now it is shifted at a point where x naught is equals to e by k. This is now the new potential profile, which is shifted. You can think it like as if it's shifted by e by k, and this is shift of e square by 2k, and the kinetic energy remains the same. So if you have to write the energy will be, we know that for harmonic oscillator it is n plus half h bar omega. For this one also it will be n plus half h bar omega and minus e square by 2k. Yeah. So just the energy is shifted by uh, DC shift is there, which is E square by 2k. Other than that, everything remains the same. And the center of the, of course, the potential has shifted by E by k, which is the x naught. Is there any question on this one? This harmonic oscillator. This is a standard question which do appear if you are willing to write any gate exam or let's say IIT exam, maybe JEST or CSIR net. These are the standard questions which will be there. They will just change the values. Either they'll give you the numerical values of the K, electric field E, and will ask you what is the DC shift, what is the position shift X naught. These are the typical questions which you will face in your coming and like exam if you are willing to participate on those. Is there any question or doubt on this one? Yeah, if there is no question on this one, then I'll move on to the next. um, I will take on the next question, which is determining the value of the commutator. So question is, what is the value of commutator AP if gradient of A, divergence of A is 0, where A is a gauge potential and P is momentum operator. So first I will uh, describe this symbol, the commutator symbol. What does it mean? So if any commutator symbol is given, then you operate it on a wave function. If no wave function is given, you select it to be the psi, right? So you, it means that AP times psi minus, or you can write it AP minus PA times psi. That's what this commutator means, this square bracket means in quantum mechanics. Okay, so not write it double, that might be confusing. It will be like this. That's what the commutator means. And now, since P is a momentum operator, so we know P is equals to momentum operator is equals to minus I h bar gradient divergence, basically del by del x, del by del y, del by del z. That's what this delta means. So you replace it in equation 1. Replace in 1. This gives you A. Okay, minus I h bar you take out common, and then you take it to be A times divergence minus P will be divergence of A times the psi, right? It will be minus I h bar A divergence of, it will operate on the psi, minus this divergence will first operate on the psi, and then again it will operate on A. So the first combination will be the A outside and the psi of this divergence operating on the psi, and the second will be psi outside and this divergence operating on A, right? So this first two term cancels each other, they are exactly the same. So the term which remains is minus psi divergence of A. Now let's look. So this will be I h bar psi divergence of A. Now let's look at the question. In the question, it's given the divergence of A is 0. So if divergence of A is 0, its value will be 0. So in short, if you take commutator of A and P and operate it on any wave function, it will give you answer 0, given the divergence of A is 0 and P is equals to momentum operator minus IH bar gradient of divergence here. So that's what it means, and that's how you evaluate the commutators in the quantum mechanics. And typically in the condensed matter, these are the kind of the problems which you'll get in your midterm or your final term exams also. Is there any question or doubt on this one? Yeah. So in today's class, we have discussed the quantum mechanics counterparts of the systems in the condensed matter, ranging from the vector potential A and how we choose the vector potential, why the magnetic field is unique for a given vector potential A, but vector potential A is not unique for a given magnetic field B, and that also gives you the theoreticians the freedom to play with the vector potential A according to the symmetry of the system to make the problem looks more easier. Although the final outcomes doesn't change on choosing the different possibilities of the A. The second question, we discussed the magnetic length and why it is important in the quantum Hall systems. And then we also discussed what happens when they cross, these magnetic lengths cross each other. The conductivity of the system increases because the bulk starts conducting now. But if they are well separated, the bulk is insulator, and then you go into the quantum Hall regime. And then we discussed about the topological insulators, where bulk is an insulator, edge is a conductor. It's a new class of the systems phases, which is of the current interest to the physicists. And in the third question, we discussed the harmonic oscillator, in which the electron is residing. And now the electron starts, basically because of this electric field, electron will feel that uh, amount of the potential energy change, and in correspondence to the potential energy change, the Hamiltonian will get modified, and that's what we see here. The Hamiltonian is modified. We solve this Hamiltonian further to understand it. Okay, how the center is shifted, how we can understand this picture, basically where the shifted center and the energies are shifted by a DC offset of e square by 2k, where small e is the electronic charge and capital E is the electric field. K is the this half k square, kx square, the prefactor of this one. And then at the final, in the question number 4, we discussed about the commutators. Like if the commutator is given, and if delta A is equals to 0, then determine this commutator relation output, what it will be for a given relation of gradient of A is equals to 0, and P is the momentum operator. So if we write the commutator as AP minus PA, so the formula generally is, if it is of AB, you write it like AB minus BA, the commutator. So that's what we did here. We wrote it like AP minus PA, and the P we then write it as minus IH bar del by del X, and we solve it, and what we get is, for the given condition of gradient of A is equals to 0, divergence of A is equals to 0, the output of this one is 0. If there are any question or doubt on this one, please ask in the comment section. Any question which is there, whether it is related to this assignment or which you are facing in your current assignment, whichever you are doing. Like if you have any doubt on the concepts, please ask in the comment section. I'll be happy to address that. Yeah, if no question is there, then we'll end the class here, and we'll have the next class on the coming Saturday. And see you guys.